All right, so this video is going to be about some general reactions with carbonyl compounds. So basically, I'm going to give you the two types of reactions that we'll see with carbonyl groups. And then we'll also go over some reduction reactions, basically. So let's take a look. We got aldehydes here, and then we've got ketones here. Okay, so these are just a couple of types of carbonyl groups. Obviously, we have our carboxylic acid, our acid chloride, our ester, as well as our amide, right? So these two different types of groups essentially are going to undergo two different types of reactions. Okay, so just real quick, you want to write this out: carboxylic acid, acid chloride, ester, and then amide. And then that R prime and the R double prime, of course, can be either the same or different. Same thing goes for that ketone group. The R or the R prime could be the same. Okay, so essentially the reason why this bottom group is going to undergo different type of reaction is because it has leaving groups. So good or bad, doesn't matter. They're still leaving groups. Okay, so when it comes to the aldehydes and ketones, they're going to be in a class of their own because hydride and R, like a negatively charged carbanion, those are just not leaving groups. Okay, so they are really bad and they would not leave. So one thing we need to remember is that carbonyl groups are sp2 hybridized. They have a 120 degree angle and are therefore planar, right? And so what we wanted to do is kind of think about how the stereochemistry of the different types of reactions that we'll see will come into play, right? So remember, anything that's usually planar is going to occur from the top or the bottom equally. The bond is also polar, so the oxygen is delta negative and the carbonyl carbon is delta positive. Okay, so generally what you'll see in textbooks is a resonance structure where you put the straight up negative charge on the oxygen and then a positive on the carbon. I don't particularly like this because technically it's not an appropriate mechanism, as the carbon doesn't have an octet, right? So that's kind of one of the rules for good resonance structures. But it is a good way of at least looking at carbonyl groups and the way they react, because that delta positive carbon is susceptible to nucleophilic attack. And so that's really what we want to take from that. Okay, so the types of reactions. For the aldehyde and ketone, we have addition reactions. Okay, so we'll have where R and R prime, they could be both hydrogen, both carbon, whatever, a combination of the two. A nucleophile will attack that carbonyl carbon because it is susceptible to nucleophilic attack, like I just said. And that puts the negative on the oxygen, followed by a little protonation from water in a second step. And that gives you this addition product where we added a nucleophile to the carbonyl. Okay, so with these bottom groups of carbonyl compounds, we have a different type of reaction, and that's going to be a substitution reaction. Okay, so really what I want to do is kind of put this as like a LG where it's a leaving group, right? Because I did say that's the difference between these. But you might see in your book where it says Z instead, where it's like a heteroatom or a more electronegative atom than the carbon. And so there is that dipole, right? So nucleophile attacks and then the leaving group leaves and you end up with a substitution there. Okay, so of course we'll get into more detail in another video for that one, but really what we want to focus on for this one is just part of the reactions for addition of a nucleophile to a carbonyl group. Okay, so let's see here. We've got the addition reaction where we attack the carbonyl carbon with the nucleophile, and then we end up with this particular intermediate where we got the negative charge on the oxygen, right? And remember, I did say that these carbonyl groups are planar, right? So that means you could attack from the top or the bottom, right? Hashtag stereochemistry. And what that results in is, sorry, let me think about this right quick. Our R and our R primed are going to be in opposite positions. Okay, so that's going to put our nucleophile at a different spot, and ultimately it's the same product, just different enantiomers, maybe. Okay, it depends if that's a stereogenic center now. But what we've got is an alcohol, right? And so that's again that oxide, or the alk oxide, the O minus, gets protonated from water in a second step. So remember that one is the addition of the nucleophile. The second step is the addition of water just for the protonation to form that racemic mixture of alcohols, okay? And that's racemic if R and R primed are different as from the nucleophile, okay? And of course, this is the addition mechanism. Let me show you the substitution mechanism, even though we're not going to go into detail on the types of reactions. I think you can easily deduce the mechanism for this, though, just based off of your knowledge of organic chemistry from all the everything, right? So one thing that I want to point out is that this can also be called a nucleophilic acyl substitution. So because that is technically like an acyl group, right? When we had the acid chloride, it was another name for that was an acyl chloride. So we've got these guys right here. Okay. Now I've changed the order of them. I wrote them in order of increasing reactivity. Okay. So as we go from right to left, we have increasing the rate of reactivity, and that's because we have increased leaving group ability, right? So if we write out our leaving groups, we got Cl, OR, OH, and NH2, right? So those are going to be Cl minus, OR minus, OH minus, which is approximately going to be equal to the OR, and then NH2 minus, right? So remember, leaving group ability has the relationship with the strength of the base, right? So increased leaving group ability as we go from NH2, the amide, to the Cl minus, because chloride is a weak base, while amide is a very strong base. Addition reactions. So we got our aldehyde and we got our ketone. Let's get that ketone. All right, so ketone capone. Oh, refresher. That's not even a word, y'all. We're talking about refresher. So we got the ketones and the aldehydes. How do we make them? What are you talking about, Jess? Like, what is this even? I don't even know how to science. So aldehydes and my ketones. Aldehydes, remember, we can hit the alcohols with PCC, primary alcohol in this case, to get our aldehyde. We can hit the alkene with a little ozone, a little DMS is dimethyl sulfide, or zinc and water. So some reducing agent in that second step. And that's going to make your two aldehydes, right? So if R is the same, that's perfect. If R is different, that's cool too. We get two aldehydes. We got an alkyne, hit that with the BH3 with hydrogen peroxide and hydroxide. So remember, BH3 was kind of like an anti-Markovnikov situation, and we end up with the enol. Remember the keto enol tautomerization? We had the enol, and we formed the aldehyde from there. Let's say we've got our ketones, right? How do we make those, Jess? Remember that time when we went over this? So we've got alcohol, hit that with a little chromium reagent, a little sulfuric acid and water, right? So that's this sodium dichromate, of course. Get our ketone. Now we can also make it from a tetrasubstituted alkene, right? Hit that with ozone, a little DMS, dimethyl sulfide again, or our zinc and water. Remember, anytime you see an elemental metal, you're reducing something, right? Because it likes to give up electrons. And then we get assuming R is the same, right? We get two of those ketones. So here, the alkyne again, if we hit that with sulfuric acid, water, and then mercury sulfate, that helped move this along, and we got our methyl ketone because, again, we formed that keto-enol tautomerization, but the sulfuric acid doesn't do the antimer-Markovnikov addition. A little benzene reaction, EAS, with the Friedel-Crafts acylation, get your benzo or your acetophenone, sorry. Okay, so those are just kind of some of the reactions. I might even miss some of them, who knows, but those are just a good amount of reactions that we should definitely know, right? So let's talk about those redox reactions. Okay, so again, this is a refresher, so lots of refreshers here, but it doesn't hurt. So let's say we have an alcohol and we do an oxidation step. That means we're forming a carbonyl, a carbonyl. And then if we oxidize that, then that means we are forming some sort of carbon Z bond. Most often there would be like a carboxylic acid. And then the reduction process is going to be the opposite, right? Okay, so another way we can actually put this like in words is if we have an increase in the number of CZ bonds and or a decrease in the number of CH bonds, then that's oxidation. Okay, and then where remember CZ is like a carbon heteroatom bond and Z is more electronegative than carbon. Okay, if we have a decrease in CZ or increase in CH, then it's a reduction. Okay, so let's really just focus on the reduction process right now. And so what we should do is introduce or reintroduce, in some cases, reducing agents. So lithium aluminum hydride, sodium borohydride, and then I like to call this, as you know, lithium chicken foot, because they got the tert-butoxide. They got 3 tert-butoxides. Are you serious right now? And then H2 palladium on carbon, dibol, and then we have our super fun enantioselective reducing agent, which is, sorry, let me just draw this out real quick because I'm about to struggle with it. Here we go. This is a CBS reagent, by the way. Again, enantioselective reducing agent. So we got the 2 phenols there, and then this hydrogen right here could be a wedge or a dash, but it's also going to have BH3 as our reducing agent, right? So that BH3 is really just interacting with this oxazoborolidine, oxazoborolidine, a CBS reagent, and it interacts with it in a manner that creates that enantioselectivity, or forces it to approach from one side of the carbonyl only. We'll get into details in that in just a second, but let's focus on the lithium aluminum hydride and sodium borohydride first, and then just a quick touch up on the hydrogen with palladium on carbon, and then we'll do that CBS reagent. The lithium chicken foot and the dibol we'll do in a different video. So, of course, lithium aluminum hydride is a source of hydride, H-, and that's because aluminum and boron are less electronegative than hydrogen, right? Better get it right. So we've got that dipole pushing towards those hydrogens, right? And so that's pretty much why it's going to react as an H-. But here's the thing, they react differently, right? So for those of you that have lab, sodium borohydride was used in lab, and it's pretty chill, right? I had that in a bottle, and we were just like, all right, throw that right inside of a alcohol solvent, and no big deal, kind of. But the lithium aluminum hydride, aluminum is less electronegative than the hydride, but it's actually less electronegative than boron as well. Okay, so it's going to be more reactive. So sodium borohydride can be used with alcohols, but lithium aluminum hydride cannot. It's more reactive, and it reacts it reacts, let's just say, immediately with alcohols as well as water, right? Where Sodium borohydride does react with alcohols and water. It's just not as rapidly. Okay, so what we want to do is use polar aprotic solvents for reactions using lithium aluminum hydride. Remember, polar aprotic could be like THF or diethyl ether. So, yeah. And then, of course, again, just writing it down for you, the lithium aluminum hydride reacts with both alcohols and water. While sodium borohydride, we can actually use alcohol solvents, which works out well because they're hella polar, right? All right, so let's take a look at the reaction and the mechanism. So the mechanism is actually pretty chill. Really what we want to do is just kind of look at it as H minus, right? Like a source of H minus as our nucleophile. And then it's very easy, right? We already established that the carbonyl carbon is the site, the electrophilic site, and is susceptible to nucleophilic attack, right? So if we hit that aldehyde with H minus, we're going to attack the carbonyl, and then we're going to make an alcohol. Sorry. Got something in my throat. All right, so same thing. If we hit the aldehyde or the ketone, we're going to attack the carbonyl group, and we're going to eventually get an alcohol. Okay, so I'm going to highlight this H from the sodium borohydride in red, and then the H from the alcohol in blue, and then just kind of label those hydrogens in the new product as basically showing where those hydrogens come from. Okay, so the same results will occur with lithium aluminum hydride or sodium borohydride, and so what you really need to understand is that they're on paper they're going to be the same for us. At least they're going to react with aldehydes and ketones in the same manner. The only difference would be like the choice of solvent if we were going to actually write it. So in the book, lithium aluminum hydride, we don't actually usually write the solvent, but throw a little THF in there and you're good to go, right? Let's just cover all bases. Second step though is water, because you want to protonate the alcohol, right? The O minus that forms as an intermediate, as we will show right here. So H minus attacks, right? That carbonyl group is susceptible to nucleophilic attack. Boom, we got that red hydrogen there from the alkoxide, which loves protons. So we'll go ahead and throw a little water in there as our step 2. Protonate that with that blue hydrogen, and now you know where it came from. Bada bing, bada boom. There it goes. Okay, so that's pretty much the mechanism, right? But of course, it's not just H minus floating around. It's going to be a lithium aluminum hydride molecule, right? I just wanted to simplify it. And we do need to kind of clarify this if we're ever going to write the mechanism. And then again, we also want to clarify that it's the same mechanism with sodium borohydride, okay? It's just more like in one step, kind of, right? We don't clarify 1, 2. We have the ethanol as the solvent, right? And then, of course, our this would be if we drew out the aluminum hydride, we would just take that HAl bond and use it to attack the carbonyl. Okay, but I just simplified it as H minus. Okay, so let's take a look at cyclohexanone with H2 and palladium on carbone. Okay, but as a little reminder, what happens when you hit it with like the methylene cyclohexane? So an alkene, we just hydrogenate the alkene, right? And we make the saturated compound, right? And samesies when you have a carbonyl. What we're going to do is throw 2 hydrogens across that pi bond, just like we would in an alkene, and then you get an alcohol, right? So pretty straightforward, right? We love when you can just write samesies for reactions, right? Same thing. We don't have to worry about it. It's really the same mechanism as well. The tricky thing is, let's say we have H2 palladium on carbon with a ketone and an alkene in the same molecule. What's going to happen? Well, it kind of depends. So let's say we have H2 and palladium on carbon with 1 or 2 equivalents. Then that's going to be a different outcome. Okay, so the reason why is because H2 and palladium on carbon reacts with carbon-carbon double bonds faster than carbonyl groups, okay? So let's say we had one equivalent. Then we can selectively hydrogenate the alkene and get the ketone product only with the fully saturated ring. Okay, let's say we have excess, like a lot of H2 platinum carbon, or two equivalents, if you will. We're going to get that hydrogenation of the ketone, the carbonyl group, as well as the alkene. Okay, so we're going to get the alcohol product. Now, here's the kicker. Let's say we have sodium borohydride or lithium aluminum hydride. What's going to happen? Well, we don't touch the alkene at all, and we only hit that carbonyl group, so we selectively form the alcohol and leave the double bond there. So we do not touch the C double bond. Oh yeah, Tia Toomey, what you know about Tia Toomey, right? She's about to flex on you. This is my flex too, because that's cool. Anytime you can selectively do chemical reactions, I love it. I love it like I love bear claws, y'all. So, first of all, like what y'all know about CrossFit, I don't know if you know about that. Second of all, stereochemistry. So we already touched up on it a little bit, right? So stereochemistry does matter, does play a role in these reduction processes because it is a carbonyl group and you can approach from the back or the front, right? Red or the pink. And if you do that, what's going to happen? Well, let's say we hit it with that pink hydride. We will approach from, well, it doesn't matter really, the front or the back. It depends on how you look at those arrows. For me, I look at it from the front with the pink and then the back from the red. So you're going to end up with these two different alcohol products. That's really the point, right? So the back and the front. But it's a racemic mixture is the point, right? And that's because this guy is planar. And so, like, in terms of statistical probability, you can approach from the back or the front equally, right? Steric hindrance doesn't really play a role. There's no selectivity. You do form a racemic mixture, okay? If you even form an enantiomer at all, right? Because it could be a symmetrical product in the end, and it's not an enantiomer, an enantiomer one way or the other, okay? So remember that one time, though, when we had these enols, so we had the allylic alcohol, and we hit that with that DET. So this sharpless oxidation process formed a single enantiomer, at least as a major product. What did I just say? It forms the epoxide as a single major product, right? One enantiomer over the other, and it just really depended on if you had the minus DET or the positive DET. So in this case, it was like a 97.5% enantiomeric excess. So this was deemed an enantioselective reaction, which is super awesome. Highly desirable when you're making things, especially if you're trying to create like drugs, whether good or bad. The enantioselective processes are highly desirable because, as you know, our bodies are like lock and keys, right? And so we only work with one particular key. And here's the positive DET reaction, and as you can see, we form a different stereoisomer. Okay, so well, where does that leave us, right? An enantioselective reduction of basically C6H5COR groups. Okay, so what is that? It's basically a benzene ring with a carbonyl group attached to it. Okay, so where R is like a carbon containing compound or carbon chain. Okay, so let's say we have this guy right here. We have the reagent SCBS. Okay, we saw this in the beginning when we listed the reagents. In the second step with water, what we're going to get is selectively this alcohol with this stereochemistry, right, with the alcohol in the back. If we hit it with that RCBS and water, we're going to get the alcohol in the front. Okay, and so again, this is an enantioselective reduction process using this CBS reagent right here. So as I told you before, that hydrogen can be in the back or the front, and that's really the difference between the S and the R CBS. Okay, so I'm cheating right here because I don't want to draw that again. I don't know what it is about heterocyclic structures, right? Rings with heteroatoms in it. They just always throw off my geometry. So the left is the S and the right is the R. And that's just the difference between basically how the hydrogen is oriented at that stereogenic center. And the CBS comes from Corey, Bakshi, and Shibata. So CBS. Okay. And these are the chemists that are, I don't know if you know this about chemists, but apparently we're arrogant and we like things to be named after us. There's literally a book that's called Named Reactions, and it's like who pretty much if you invented it, then you name it after yourself. I don't know. I don't know what I would do. I'd probably name it after my kids or something, or like my dog. Or maybe I would change it up and just like I'll name it like the LeBron reaction if it was like the GOAT reaction. You know what I mean? Because LeBron's the GOAT. Don't argue with me, okay? I don't want to talk about it. He's like, how many years in the NBA? He's still balling out of control. Are you serious right now? Not even slowing down? Like, for real? Like, that's crazy. He's not broken down and tired of living life on a merry-go-round. Ooh. JK. I'm just saying, like, he just continues to rise up. Rise like the day I'll rise up. I mean him. He rise unafraid. Oh my God, I'm going on my tangent real gig again. I do too much. I gotta keep myself entertained, and everything, like I said, leads to music. Anyway, here's the CBS reaction. Just so you know, it can do lots of things. Even no matter what those R groups around, it's going to do a variety of things. So what you really need to know is about this guy. So nicotinamide adenine dinucleotide, aka NADH, right? So if you took bio something or other, then you probably this is a crazy molecule, right? So we really want to focus on the thing on the left, right? So it's useful for reducing pyruvic acid to lactic acid, right? So when you're doing when Arnold's trying to bomb you up, get out of here, and then you're just like, all right, Arnold, I got this, and you're like, rah, what do little kids and Arnold have to do with one another? Any chance I get, I'm about to throw kindergarten cop at you, all right? So shut up, get out of here. It's not a tumor. Okay, so anyway, NADH is used for the reduction of pyruvic acid, and we really want to focus with this thing on the left. And so reduction of pyruvic acid is going to result in lactic acid, and we're only going to form one enantiomer because the body is amazing and it's much better than the reactions that we can do in the laboratory. So if we take pyruvic acid and reduced it with this portion of the molecule, NADH, then what we're going to do is essentially treat it as a source of H minus, right? Just like we did with the sodium borohydride and the lithium aluminum hydride. So the H minus comes from, I always mess up that ring, that heterocyclic ring, like I told y'all. So let's put that nitrogen there. So the two hydrogens on the end, that's going to be the source of the hydride, okay? And the reason why this works well is because once we attack that carbonyl group, we lose that hydride and we actually form an aromatic ring, okay? But anyway, I'll show you that in a second. We have the hydride attacking with some source of acid. We will protonate and to make the alcohol, okay? And so this is the enantiomer of lactic acid. So like I said, pyruvic acid gets converted to lactic acid, and this is actually in the if we don't have sufficient oxygen. So if you're working out with Arnold and he's just getting crazy and pushing you too hard and you feel that burn that burn is lactic acid, and that's usually when you've kind of surpassed your lactic acid threshold and you don't have sufficient oxygen, and so it's under anaerobic conditions essentially. And the cool thing is that this is 100% selective, right? That's, again, the body is amazing, and we really just hope to achieve this type of selectivity in the lab, or at least as close as we can get, and it never really works out. Okay. Let me write this: lactate dehydrogenase. Got to give credit to the lactate dehydrogenase because it is also, I mean, that's really where this is occurring. It's the enzyme, right, involved in this process. This is, of course, the source of NADH. Once you lose that NADH, you form NAD plus, right? So again, if you've taken biology courses where you talk about like glycolysis and all that good stuff, you probably talked about NADH. And so the way it works is you use the lone pair on the nitrogen to kind of push those pi electrons to force that hydride to leave. Again, it's not a leaving group. It's more of like you can think of it as like a concerted reaction, right? So that hydride attacks, and then what ultimately results in the aromatic ring, right? So this N plus, right? That's where the NAD plus comes from. And you have this amide sticking up here, and that almost like a pyridine ring, right? So there you have it. That's where that's what we get when we throw a little NADH at pyruvic acid. You got to feel that burn, y'all. All right, I don't have jokes for you per se, but I got some running memes because I like to run. And it's not bragging when I tell you how many miles I ran today. It's so you don't judge me when I devoured this whole bag of chips. Okay, so I ran to eat. You know you're a runner when the thermometer says 45 degrees and you think, score, optimal running weather. Or you know you're a runner when it really bothers you that regular people don't know the distance of a marathon. They assume all races are marathons. Like, get out of here. Come on now. For my kids, good. Let the lactic acid flow through you. I think that's like a Star Wars dude. I don't know. They like Star Wars now. I'm super bummed about it. Lactic acid, more like a milky body wash for my inside. Some people like the burn. I'm one of those. I like to know that I got some work done. So, yeah, that's pretty much it, y'all. That's reducing reagents and reactions with carbonyl groups. Have fun. Let me know if you have any questions.